Imagine standing in an empty field. Your task is to turn that dirt into a colossal industrial facility, operating safely for decades. This graphic shows two main ways to approach a project. On the left is a greenfield project, starting entirely from scratch on unused land. On the right is a brownfield project, involving upgrading an already existing facility. Starting in a greenfield gives you total freedom to design whatever you want without tripping over old pipes and buildings. But that freedom comes with a trade-off. Before you can manufacture a single product, you must spend significant capital to build the basic infrastructure, like power grids, roads, and water lines. This S-curve timeline starts with planning, climbs through engineering, and plateaus during construction. Focus on the light blue early phase. While costs are low, it's critical. Decisions made here lock in 80% of the massive capital expenditures realized later. This diagram breaks down the first big decision, picking the site. You must analyze the soil to ensure it holds heavy buildings, guarantee a permanent water supply, access stable power grids, and find highways close enough to bring in raw materials. Choosing a location with poor soil or an unstable power grid creates permanent operational problems. You cannot fix a bad location with clever engineering later on. Once you have secured the right piece of land, you need to collect a mountain of data to build your master blueprint. Engineers surround this campus map with essential data, calculating process chemistry, electrical loads, and local weather patterns. But machines don't run themselves. Looking right, you must design a supporting campus for the human workers, including cafeterias, medical centers, and fire stations. A modern plant is a self-sustaining city. If you focus only on the machinery and forget to map out where the workers will eat or park, you will eventually have to rip up your carefully planned layout to make room for them, bringing construction to a halt. To translate chemistry into physical steel and concrete, engineers use two distinct levels of blueprints. This process flow diagram on the left acts as a simple sketch, using basic blocks to prove the core chemistry works. On the right, the piping and instrumentation diagram is the master rulebook, mapping out every single pipe, valve, and safety sensor in the facility. You cannot order raw materials or legally prove your plant is safe based on a rough sketch. That hyper-detailed master rulebook is legally binding, and every contractor relies on it to do their job safely. This diagram shows how a flat 2D blueprint translates into physical 3D reality. Notice the red box on the right. Engineers must leave substantial empty space in the 3D model for maintenance crews to pull out internal parts, otherwise walls must be torn down. This exploded 3D view breaks down the piping elements. Straight pipes act as arteries, curved elbows change direction, and reducers squeeze fluid. On the right, thick metal flanges and gaskets create high-pressure seals, while valves act as giant faucets controlling the flow. Arranging these parts accurately in 3D space ensures they won't crash into one another during construction and guarantees your maintenance teams can actually reach the valves in an emergency. Building the plant is only half the battle. Once you turn the machines on, intense heat causes solid steel pipes to stretch lengthwise, while internal fluid pressure aggressively pushes outward. This 3D computer model shows how engineers predict where that heat will cause damage. Before a single piece of metal is cut, software simulates the temperatures and highlights exactly where the pipe is likely to crack or break under the stress. This 4-panel graphic shows how engineers manage dangerous forces by installing mechanical supports that allow steel to move safely. In the top examples, extra pipe length forms a U-shaped loop absorbing heat movement, while heavy-duty spring supports soak up severe vibrations. You cannot stop steel from expanding when it gets hot. By anticipating the physics and designing flexibility directly into the system, engineers keep those high-pressure lines from rupturing. This interlocking gear diagram represents the entire facility. Designing a plant requires multiple engineering disciplines to constantly share information. If the chemical team changes a temperature, the mechanical team redesigns pipes, and electrical supplies more power. If teams stop talking, the gears jam. This summary slide breaks down the actions that lead to a predictable reality: thorough site selection, design validation, and structural integrity. Building from an empty patch of dirt requires a large financial leap. By using rigorous data, strict blueprints, and seamless teamwork, Engineers take that initial capital risk and transform it into a highly predictable, reliable operation.